speak here. So it's great to speak at this beautiful venue and great series. So I'm going to talk about formulating emergence in the physical science. I'm going to give a formulation of what we mean when we say emergence. So it's going to be a philosophical talk. So the aim is to introduce a criterion for emergence and also to illustrate it. It will be a formal criterion, where by formal I just mean that it uses the notions of, or it allows and uses the notions of maps and sets. So formalization here is not a goal, but it's rather a tool that we use. The goal is to really be able to analyze examples in physics. And the examples that I'll do today will be relatively simple, so, but hopefully the framework can also be, the criterion can also be applied to other examples. So the framework will emphasize emergence as being an interpretative rather than a merely formal relation between theories. So that will be my key message. So I would like to discuss ontological emergence. In the literature, there are distinctions between different kinds of emergence, ontological emergence, epistemic emergence, and other kinds. Here we'll focus on ontological emergence, but I should say that the aim of the project is not strongly metaphysical, in the sense of being committed to a particular metaphysics of the world and analyzing emergence in those terms. Rather, I want to keep the framework as general as possible, and just to clarify what we mean by ontological emergence in general, and to give a criterion that is as straightforward as possible. So I wish to give a minimal account independently of, for example, whether we are Humeans or Aristotelians about causation, and one can add further metaphysical details and discussions to the framework in a later stage. Because one danger that I wish to avoid is to make the conception of the framework conception of emergence dependent on very specific metaphysical notions. So I will understand here ontology in the straightforward sense of the ontology of a scientific theory. So the domain, it will be the domain of application that a theory describes under a given interpretation. That will be the ontology of the theory. Now, this domain of interpretation will be a part of the empirical world. It will not be just a matter of language in Quinian fashion, but rather it will be a part of the world. So here's the outline. I will start with a brief review of emergentism. Then I will introduce a framework for emergence, and then I will give two examples. Two examples actually. So emergentism goes back to at least C.D. Broad. In 1925, he gave one of the very influential definitions of emergence. He says, put in abstract terms, the emergent theory asserts that there are certain wholes composed, say, of constituents A, B, and C in relation R to each other, that all wholes composed of constituents of the same kind as A, B, and C in relations of the same kind as R have certain characteristic properties. That A, B, and C are capable of occurring in other kinds of complex where the relation is not of the same kind as R, and that the characteristic properties of the whole cannot, even in theory, be deduced from the most complete knowledge of the properties of A, B, and C in isolation, or in other wholes which are not of the form R, A, B, C. So this has been an influential, and it has shaped part of the discussions in emergence certainly until the 80s. But it has its drawbacks, as actually Broad himself already points out, that he cannot give a conclusive example of emergence because he's not aware whether this definition actually applies to anything in physics. So this is something that he himself admits. And in fact, more recent accounts of emergence since the 90s and the 2000s have attempted, rather than defining emergence in terms of something negative, like lack of deducibility, right? They have focused on positive accounts. giving different controls of the motion of the notion. So here's some of the recent literature on this topic. And I suppose Karen will later also talk more about it. So the recent new way of emergentism since the 90s goes back to a discussion between Anderson and Weinberg. So in a paper in 1972, Philip Anderson wrote the following. So the laws and principles he studies as condensed matter physicist are emergent in the sense that they are entirely different from, but have no lower status than those studied by particle physicists. So that was kind of the bone of contention, whether, say, particle physics is more fundamental or whether condensed matter physics is more fundamental or at least as fundamental as particle physics. And Anderson he begins his paper saying that he accepts reduction, but not constructionism. What does he mean by constructionism? So he says, the reductionist hypothesis does not by any means imply a constructionist one. The ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. The more the elementary particle physicists tell us about the nature of the fundamental laws, the less relevance they seem to have to the very same real problems of the rest of science. Of course, Steven Weinberg, who was also a Nobel Prize-winning particle physicist, he replied, writing that the physics of the very small hold a privileged position in a hierarchy of scientific explanation. So the debate was taken to the US House of Representatives over the funding for the superconducting supercollider that was going to be built. Actually, they started building, but they didn't finish because of lack of funding. So Anderson wrote, I emphasized the almost complete irrelevance of the results of particle physics, not only to real life, but to the rest of science, while arguing that they are in no sense more fundamental than what Alan Turing did in founding computer science, or what Francis Crick and James Watson did in discovering the secret of life. So Anderson's point of view is clear that these higher level sciences are for him as fundamental as elementary particle physics. Weinberg, on the other hand, wrote, one of the members of the SSC board argued that we should not give the impression that we think that elementary particle physics is more fundamental than other fields, because it just tended to enrage our friends in other areas of physics. The reason we give the impression that we think that elementary particle physics is more fundamental than other branches of physics is because it is. I do not know how to defend the amounts being spent on particle physics without being frank about this. So he argued for the SSC funding from a reductionist perspective, saying that, yes, particle physics is more fundamental, therefore it should receive more funding. Now, the argument didn't make it very far because the project was discontinued in 1993. So I would like to, kind of get away of this discussion between, on the one hand, reductionism and constructionism, and just look at emergence as it appears in physical systems. So emergence is a ubiquitous phenomenon. It is roughly the observation that there are high-level phenomena or also entities and theories that appear in the macroscopic world and which are absent from the lower level or microscopic world. So usually it is, emergence is seen as a balance between two different aspects. On the one hand, dependence between these two levels, or we could also call it linkage, or slightly differently, rootedness, it's sometimes called. And on the other hand, independence, or sometimes we'll talk about autonomy and also novelty. And various construals of emergence use, these various characterizations. I will discuss emergence here in terms of theories. I will say that theory X is emergent with respect to theory Y. But this can also be put in terms of entities, properties, or behavior. So I will endorse this rough definition of emergence, and I will focus on novelty and on linkage. So one thing that I will not emphasize in my talk is the question of mereology. So like in the discussion between Anderson and Weinberg, discussions about emergence are often about making things up from parts, right? So building stuff from the micro level to the macro level, kind of putting things together and making something bigger. Now that's a very interesting case, and eventually we would like to tackle that problem. But for a moment, I'm going. My examples are not going to engage with that because I think that this example easily leads to confusion. So the kind of emergence I will concentrate on could be called conceptual. So it will be emergence of theories, entities, properties, or behavior that we link in different situations or systems through a relation of resemblance, which I will call linkage. And I should add that I expect that the framework can also be applied to mereology as well, but it will not be my focus here. Now, another thing that is often emphasized in discussions of emergence in the philosophical literature is, especially in philosophy of mind, is the question of causation and powers. So the ability to cause phenomena from, say, the micro level. However, the new wave of emergence in physics that I was talking about has not focused on this kind of emergence. Rather, it has focused really on the emergence of entities and emergence of theories. Perhaps because the notion of causation itself comes less naturally in, say, quantum physics than it does, for example, in Newtonian physics, where we kick a ball and we see how we cause it to move. So that's another aspect that my discussion will not go into at the moment. So to give you an example of emergence, a well-known example that has been discussed a lot in the literature, and I think it's widely accepted that this is indeed a good example of emergence. So consider an iron bar in a strong external magnetic field parallel to the axis of the bar, and we are at low temperatures. Now the bar, because of the external magnetic field, will be almost completely magnetized, so the electrons have a spin, and the spins will point in the same directions. Now we decrease the temperature, we decrease the external magnetic field to 0, so we remove the external magnetic field. If we are at low temperatures, then the magnetization will remain. It does not decrease to 0. So we have the phenomenon of spontaneous magnetization that we are familiar with magnets. Also, if we do the same but reversing the direction of the field along the axis of the magnet, then we will get the reverse magnetization, so in the opposite direction. Therefore, qualitatively, the magnetization as a function of the field can be drawn something like this. So here's the magnetization, the y-axis and the x-axis is the magnetic field. You see that for a positive field, there is a high magnetization. It drops, but it doesn't drop quite to 0, but to some m0 at 0 magnetic field. So that when the magnetic field is 0, there is a finite magnetization left. And then, because of this argument that the magnetization should reverse sign if we reverse the external field, we will get the mirror image on the other side. Now that implies that here there is this kind of jump at h equals 0. Now, what happens if we increase the temperature? Well, if we increase the temperature, we would expect that the molecules will randomize due to the energy that they get from temperature. So there is no net magnetization left. They will just point in random directions. And so when we remove the field, the magnetization will go smoothly to 0. But experimentally, there is a critical point at which this graph and the previous one go over into each other. That is the critical temperature where basically the tangent here is vertical. So that's the so-called Curie point of the ferromagnet. So we can define this the spontaneous magnetization as the limit of the total magnetization when the field goes to zero. Now, if we draw the spontaneous magnetization as a function of the temperature, then this is what we find. So above the critical temperature, the magnetization is zero, so the molecules are randomized. There's no spontaneous magnetization. But if we are below the critical temperature, then we do get magnetization, which goes from 1, so 1 meaning that all the spins are basically aligned in the same direction, and decreasing continuously to zero at the critical temperature. Okay. Now this here, to study this region over here, the region near the critical temperature, you can imagine that that's a region where something interesting happens. One way to look at that is to analyze what people call critical exponents. So to expand basically the magnetization in powers of this parameter T, which is just the difference between the temperature and the critical temperature relative to the critical temperature. It's a parameter that tells us in units of 1 how close we are to the critical temperature. And then it's this exponent here that is of interest, that contains the dynamical information about the model that we are looking at. And those exponents can be calculated in a variety of ways, using the Ising model or using renormalization group techniques. Here I will focus briefly on the so-called two-dimensional Ising model, which is it's basically a simplification where you imagine that rather than having a three-dimensional magnet, we have just a two-dimensional surface. So it's a two-dimensional plane where where we have a lattice with, at each side of the lattice we have a molecule or an electron with a spin that can point up or down. Now this model was solved exactly by Onsager in 1949, so it has a beautiful description, beautiful solution, exact solution, which is written here, below the critical temperature. So this parameter K is just 1 plus that parameter T, so it's basically just the temperature divided by the critical temperature. And if we are below the temperature, the critical temperature goes between 0 and 1. So you see that this curve over here is this curve over here. If you plot that, this is the kind of plot that you get. And you see that indeed, when K goes to 1, which is when T goes to the critical temperature, that factor goes to 0 as expected. Now there is an interesting quantity that you can calculate in this model, which is called the correlation length. So the correlation length roughly tells you how two spins on different lattices are correlated. So if you calculate the average magnetization of two spins separated by some distance, then you will find that on average these spins are correlated, and the correlation length is roughly tells you how this correlation decays in space. So at long distances the correlation gets lost, so that spins point in different directions. But if the spins are close to each other, are short at distances shorter than the correlation length, then the spins will be correlated because of the spontaneous magnetization. So this correlation length turns out to diverge at the critical temperature. So you can calculate it also exactly, and if you expand it around the critical temperature, you see that it goes to infinity, which means that basically at the critical temperature, all the spins of the lattice, the entire lattice, they are all correlated. So it's a macroscopic phenomenon. It's just another way of saying that we have this spontaneous magnetization where there is a macroscopic non-zero magnetization in the ferromagnet. So the system is macroscopically ordered. Rather than every spin pointing a random direction, there is a definite direction which has been induced by the external magnetic field. Now, in a real ferromagnet, by the way, this point h equals 0 is often regarded as a phase transition because magnetization changes suddenly from negative to positive. Now, in an actual experiment, this discontinuity is smeared out, and the phenomenon of hysteresis occurs. I just show the plot. I'm not going to focus a lot on it. Basically, here's the magnetization. Here is the external field. What happens is that rather than having the curve that I had before I had a single curve. Remember, it went until here, and then it decreased, and then it continued here. Now the curve is being smoothed out, and actually we get two curves. So the material has a kind of a memory that it remembers where it came from. So if it comes from here, then it follows this path. But then if you increase the field again, the external field, it takes this path rather than the other one. So that's the phenomenon of hysteresis. Now, at the critical temperature, we have the appearance of order, this given by this macroscopic correlation length, and of spontaneous magnetization, so a non-zero magnetic field of the material when we remove the external magnetic field. Now, so why do people say that this is a case of emergence? Well, I think it is a striking case of emergence because the properties at Tc are novel relative to those to the properties above the critical temperature. Namely, we have non-zero magnetization, we have spontaneous magnetization, and we have a macroscopic order. We have an infinite correlation length. So these properties fit the informal description of emergence that I gave earlier in terms of linkage between the model at the critical temperature and the model at above the critical temperature. So we do have these two levels. So we are comparing two phases of the material. And we also have this novelty at the critical temperature. So that's why this case is widely regarded as emergence. Now, in the rest of the talk, I would like to go in slightly more detail into how to define emergence. Now, to characterize emergence, some authors have emphasized the mathematical properties, strange mathematical properties of this model that I showed, like, for example, this discontinuity that you have when the magnetic field vanishes, or this jump of the field. Yes.
So you get an order parameter, is that right?
Yeah.
And that's the emergent quality.
Yeah, that's one of the emergent
properties.
Yeah. So the order parameter is one. Also, the spontaneous magnetization is also a novel phenomenon. Yeah. So some authors have focused on those mathematical discontinuities and infinities. And those are admittedly important, but I think they're not essential for emergence. Why not? Well, because after all, these strange mathematical properties are idealizations. Some of the emergent behavior might already be there before we reach the critical temperature, for example, because of the presence of impurities in the material. So we would like a characterization of what we mean by novel properties and behavior that, on the one hand, stays close to what Batterman here has in mind when he talks about these discontinuities, but on the other hand, that it doesn't rely on on very specific mathematical properties of specific models. Rather, what I would like to focus on is the change of interpretation that appears when you have the novel behavior. So we have these novel phenomena, and those novel phenomena prompt us, are basically a change of interpretation of the theory, as I will now explain in the next few slides. So I would now like to make a proposal for how to formulate emergence, but first we have to talk about what is a scientific theory, because it will be important to have at least a rough idea of how we think about theories. Because we will talk about emergence of one theory from another, as well as emergence of phenomena. So the main point is to distinguish a bare theory from its interpretation. So what do I mean by a bare theory? So a bare theory is basically, you could say, just the mathematical formalism of the theory. It's the formal structure of the theory with a set of rules for doing calculations, for forming sentences. It's like an abstract calculus. It doesn't yet have a physical interpretation that allows me to go to the lab and do an experiment. So typically, this bare theory comes as a set of axioms, a set of equations, summary side. Often it's what we call the laws of the theory. Although laws often already suggest an interpretation, but you can also look at the laws themselves just as a system of axioms. So to be specific, the framework considers bare theory as a triple of a state space, a set of quantities and a dynamic. So we have, on the one hand, states, like, for example, position and momenta. We have quantities like energy, and we have a dynamics, such as Newton's equations. So that's what we call the bare theory. The interpretation adds to the bare theory what we call a reference. So it says what the elements of the bare theory correspond to in the world. And actually, this later on, Jeremy Butterfield will talk more about this. So we envisage a referential semantics using interpretation maps on states and quantities. So I said that the theory contains a set of states and a set of quantities. And on those sets, we can put maps to the world. And that's how we interpret the theory. So we assign values as outputs of maps that are parts of the empirical world. They are in general partial maps because not every state or not every quantity necessarily has a reference. So for some arguments, the map might yield no value. And so we can summarize it with this notation. So the interpretation map is a map from, is a partial map from the theory to a domain of application in the world. And remember that T is the bare theory, it's the calculus, and D is a domain in the world. Now the domain, I will regard the domain as a structured set containing elements or objects and relations between those elements. So to give an example, a very simple example. Consider Newtonian gravitation. The bare theory is as follows. So here are Newton's laws, Newton's second law, F is m times a, and then the law of gravity for two point-like masses. Now, so far, this is just a set of laws. This might describe Newtonian gravity, but it might also describe an economic system. This becomes Newton's law when we give an interpretation. So we write down this map saying, well, the symbol F stands for the gravitational force, M stands for the mass, and A is the acceleration of the body, where we are assuming that these items over here, these are items in the world. So we're assuming that we already know what we mean by gravitational force with mass, and so on, in the relevant domain in the world, for example, in the solar system. Now this, of course, a very simple interpretation, even simplistic. For a more elaborate interpretation, one would need to spell out in more detail the domain, also a particular context. For example, one would say not just the gravitational force, but one would say this represents the gravitational force between the Earth and the Sun, and one might even give a procedure for how this force can be measured. But this is the basic idea of having this interpretation map from the theory, from the laws, to the world. A few comments on interpretation. So this conception of a theory is meant to make a clear distinction between, on the one hand, the formal aspects of the theory, and on the other hand, the interpretative aspects, which are mostly non-formal because they regard They are conceptual, they regard also experimental issues, and so on. So the maps being non-injective embodies the idea of coarse graining to describe a physical situation. So non-injective means that several elements in the bottom theory can be mapped, will in general be mapped to the same element in the top theory. So it is not a one-to-one map. And this captures the idea of coarse graining. In coarse graining, what you do is basically you have a microscopic state or set of states, but those states are so similar to each other that they all basically correspond. If you're looking at the macroscopic level, they all correspond to the same macroscopic state. They give rise to the same macroscopic state. So that's the idea of coarse graining, and this is captured in this map link. Okay, so let me say a bit more about this first condition of linkage. It will, in general, combine three properties. It could be, and it will often be a limit in the mathematical sense. So this linkage map will often be a limit when we have a parameter in the bottom theory which we take to some special value. For example, if you take quantum theory and you take h bar Planck's constant to 0, you get classical mechanics. Or if you start with, say, special relativity, take the speed of light to infinity in a certain way, you also end up with classical mechanics. Or sometimes you want to start with statistical mechanics, take what people call the thermodynamic limit, so you take the number of molecules to infinity and fix the volume and densities in certain ways, and you get thermodynamics. So those are limits that correspond to this idea of linkage. Now, a second property of linkage will often be that while we take one of these limits, we also compare different physical situations or systems. So if we take h bar to 0, for example, we are not only doing something formal. While we take h bar to 0, since h bar is a dimensional full quantity, we also need to take some other physical parameters in the theory to 0, usually the action. So you have to, and in changing the action, you are actually changing your system, or you are following your system through a set of changes. So these limits that we are considering here are not innocuous. A very clear case of that is taking n to infinity. Taking n to infinity is a physical limit of adding more, considering systems with ever more and more molecules. So you are clearly comparing different physical situations, namely a system with few molecules and a system with a lot of infinitely many molecules. This will soon prompt further distinction based on work by Norton on two different ways to look at this. The third one is mathematical approximations. We'll skip this one because we will not need it in the rest of the talk. So to give you an example of linkage, and remember what I'm doing is I started saying there are two conditions for emergence. The first is linkage. The second will be novelty. Now I just defined what I mean by linkage, and now I'm going to give an example of that. So consider the link between special relativity and classical mechanics. So classical mechanics can be obtained as a limit in which we take, as I said, the speed of light to infinity, c to infinity, compared to all the speeds, all the other speeds in the theory. Because again, c is a dimensional full quantity, so we have to take it to infinity relative to other quantities in the theory. What are those quantities? Well, the speeds of the particles. So we have, therefore, that our basic theory is special relativity, our top theory is classical mechanics. And the linkage relation is like as written here. So if we take the linkage map on the bottom theory, that is the same as taking the limit c going to infinity in this way that we've mentioned, and that gives us, as a result, classical mechanics, at least for the sets of configurations that we are looking at. So that means that for each formula of TB, we get a formula of TT. But notice that the map is not injective, because the information about C is washed out in this limit. So if the speed of light was 300,000, or maybe it was 100,000, TT doesn't remember, doesn't contain that information anymore, because we have taken the limit. We have gone through a series of theories. So different formulas in TB, so this TB actually contains a set of theories that give rise to the same formula of TT. So therefore, this is what I meant at the beginning by saying that this was a non-injective map. So a formula. So there will be different formulas in TD that will give rise to the same formula of TD. Also, like I said before, when we are doing this, we are comparing different physical situations and systems. Now that I have defined the first aspect of emergence, I want to go into the second, novelty of reference. And here it will be useful to introduce distinction by Norton. So Norton distinguishes approximations and idealizations. He says an approximation is an inexact description of a target system, while an idealization is a real or fictitious system distinct from the target system, whose properties provide an inexact description of the target system. So both approximations and idealizations provide inexact descriptions of the target system. The target system is a system we are interested in, but they do so in different ways. An approximation just gives an inexact description. That's it. An idealization, in addition, has the condition that there must be what he calls an idealizing system. So there is some other system, whether it's real or fictitious, whether it's the system itself or some other system, that whose properties provide an inexact description of the target system. So here we are comparing our target system with the idealized system. Here we are not. Here we are just, say, doing an approximation, calculating some quantities, but we are not dealing with an idealizing system. So Norton summarizes the difference between the two as an answer to the question, do the terms involve novel reference? So here there is no novel reference because there is only one system, there is only the target system. In the case of an idealization, there is the target system, and there is or there may be the idealizing system, and that idealizing system may have novel reference. So there is novel reference only in the case of idealization. So my proposal for novelty of reference is to define ontological novelty as novelty of reference, sorry, the other way around. So my proposal for ontological novelty is to define it in this way as novelty of reference. So this will restrict the kinds of linkage maps that I'm allowed to use to only cases of idealization. So cases where the linkage map doesn't just spit out some theory, but it spits out a theory that actually corresponds, that has a reference, that corresponds to an idealizing system. And that is, in fact, a far from trivial requirement. And Norton has shown this in recent work with some examples, and in my own work I've also seen that indeed, very often, if you just take some linkage map, very often you don't end up with a system that has necessarily a reference. Okay. So to be slightly more precise about the notation, so I have these two theories, and I just said that each of them has its own reference, right? There is novelty of reference. So each of them is going to have its own interpretation. So I have an interpretation map IB and IT, and two domains of application DB and DT. So the novelty comes in when there is novel reference in this theory, so this domain is different relative to that one. So you see that we have these two natural conditions, these two cases. Either the two domains are the same or they differ. you could weaken that, but I will not consider that. So let me look at the first case, the case of same domains, where our bottom theory and our top theory, the bare theories are different, but the reference is the same. So the domains of application are the same. That means that the elements and relations are the same between the two domains. So in this case, there can be, according to my definition, no ontological emergence, because there is no novelty in the world. There is just a single domain. So the theories describe the same items. They may do that in different ways, using different formulas, but it is the same domain. Now, since I'm interested in ontological emergence, I will leave this case aside. So this is not the case that we are interested in. The case we're interested in is the case of different domains. So at least some of the elements and relations differ between the two domains. And the more the domains differ, the more significant the novelty. So novelty comes in degrees. So this is my proposal for a criterion of ontological emergence, and it's, I think, a rather commonsensical proposal that novelty of reference, so ontological emergence entails, as its second condition, novelty of reference expressed as a difference between the domains related by the linkage map. So you can summarize this, what I have just said, in this diagram over here. So we have the bottom theory and the top theory related by the linkage map between the two. Each of them has its own interpretation, its own domain, and these domains are not identical. They are not the same, so that's why this upward arrow here, which has this E for emergence, is the emergence arrow, you could say. It's not the identity. It's not the identity arrow because the two domains are distinct. Now we can so this is my condition for emergence, that this arrow is not the identity arrow. We can translate that in terms of our notions, specific notions for this theory that we can introduce. We can translate it into a criterion for this map. Namely, that if we, this is what is called a non-commuting diagram. So if I start from the bottom theory and interpret it first, or and then I compare it to the top domain, or I first take the linkage map and then interpret that theory, I will end up in a different place. So this arrow over here doesn't end. So this path over here is not the same as that path. So that means that the composition of these two maps is not the same as that map. So there is a non-trivial comparison to be made over here. So in case this translates itself in a natural way, so this is looking just at two theories, but in cases where we have a limit, so we have a one parameter family of theories, then we define the top theory as the limit of x going to 0, and then we can rewrite this criterion in the following way, so that basically the bottom domain at x equals 0, when we take this parameter to 0, is not the same as the range of the interpretation map of the top theory. Yep.
So you wouldn't consider classical mechanics and special relativity to be an example of ontological emergence?
I would, yeah. Yeah, because there will be notions, for example, this theory, classical mechanics, will have a notion of simultaneity, which doesn't exist. So absolute simultaneity, it might have the notion of absolute space, which will not be over there. So this theory will have additional notions. So, but that's actually a good question, because yeah, you have to work out, in each case you have to work out these maps, and that's actually what I'm going to do in my next examples. So as an example of ontological emergence, and you should tell me how I'm doing with time, 5 minutes? Yeah. So we'll go through this example quickly. So I will take an example from classical physics, emergence of masslessness. a theory of point particles with respect to a theory of massive particles. So it illustrates, in a simple setting, a widespread phenomenon in physics, namely the existence of a massless, or if you wish, scale invariant regime within a massive theory. And this is often done using renormalization group flow or phase transition. Here I will consider a very simple example of obtaining massless particles starting from massive particles. And what I wish to say, to show, is that the massless regime is characterized by different symmetries and different geometrical properties than the massive regime. Now here are the equations of motion for a massive particle in Minkowski space. So I take this to be my basic theory. Now, we have to interpret these equations. So, and the natural interpretation is that, for example, x mu as a function of tau corresponds to the position of a massive particle with mass m moving freely in Minkowski space as a function of the particle's proper type. So that's the usual interpretation. Now notice that if we look at a massless particle, the interpretation changes. So if we take m to 0 and interpret those equations, the interpretation will change. The interpretation will be something like the position of a massless particle moving at the speed of light in Minkowski space as a function of the affine parameter of its world volume. So you see two changes. We have, rather than having a massive particle, now we have a massless particle. And second, we no longer have the notion of the particle's proper time. We only have the notion of an affine parameter on the world of light. So we get different. So the interpretations of these theories are different. So here in this slide, I say it slightly more precisely, but it's basically just saying the same thing again. So the bottom theory is those two equations that I showed for the particle of mass m. That's the bottom theory. Now the linkage map, if I take the linkage map, I take the limit, gives me the top theory. What I get is just that same theory for the particle of mass 0. I just insert that value of the mass in those equations. Now what is the interpretation? The interpretation of the bottom theory is a free massive particle of mass m. And like I said, the interpretation of the top theory is a free massless point particle. So the interpretation of the top theory is different from the one that we get by setting m to 0 and interpreting. So if I first set m to 0 and then interpret, I get, or I first interpret and then set m to 0, I get two different things. So here is what I get from equation 6, so from that free massive point particle, right? And now I insert the value 0 in my interpretation. So I first interpret and then set m to 0. Or here, I compare it with what I get if I first set m to 0 and then interpret. What I get in that case is a free massless point particle. So I get two different things. So what I want to argue next is that these two things are not the same. Therefore, the order in which you do the things matters. So the underlying point that I'm making is that a free massless point particle is not the same as a free massive point particle of mass 0. In fact, this is one of the concepts that don't refer. This is a concept that doesn't really make sense, as I want to argue next. But this is just an illustration of this diagram. So I have shown that setting m to 0 and then interpreting, you get here, first interpreting and then setting m to 0, you don't get here. You get to some other place, to this. You get to this place, which is basically doesn't exist. So here is in view of time, I think I will skip this, but here was the detailed argument why a free massless point particle is not the same as a free massive point particle of mass 0. I mean, the phrases look similar, but the basic point is that a massless particle has different symmetries than a massive particle. And the symmetry group of the massless particle is not a subgroup of the symmetry group of the massive particle. Therefore, we're really dealing with different kinds of objects. And there is a similar argument to be made for the geodesics, but in view of time, I will skip that. You can look at more detailed situations where you look at, again, starting from the basic theory, collision of two particles moving in the same direction. So I shoot two particles with an initial difference in time interval. But the second goes faster than the first, so it will overtake the first, they will collide. Now if I take the massless limit of this situation over here, the two particles will both travel at the speed of light and they will never collide. In other words, the crossing point is pushed to infinity in the limit. And so the interpretation of these two diagrams is really different. So as long as the mass, so there is a question that you can ask in this theory, namely, will two particles coming from the same direction collide? You can ask this question in the interpretation of the two theories, and it gets a different interpretation, a different answer. So as long as the mass is non-zero, they will always collide within a finite time. For m0, they will never collide in a finite time. So this is, again, a case of a bare theory whose interpretations ascribes contradictory properties to the limit system, namely a free massive particle of mass 0 is something that doesn't refer to anything. So there is, in other words, no limit system described by IB. If you want to get the limit system, you have to really go back to the top theory and interpret that directly. So you have to construct the top theory's interpretation. Okay, here are a few remarks about. So this has been my basic criterion for emergence, for ontological emergence. Now here I have one slide or two on why this is ontological emergence. I will just say that so the way I use the phrase ontology is in the framework of intentional semantics. You have, so intentional semantics appropriately models the interpretive practices of both realists and empiricists. So whether we are realists or empiricists, we can talk about the ontology of theory in the same way. That's kind of the consensus in a consensus in philosophy among philosophers and science since Van Fraassen. So he called it the picture of the world drawn by the theory, and how realists and constructive empiricists can both agree about the interpretation of a theory or model, even though they have, of course, different degrees of belief in the entities that the ontology of the theory postulates. So we can talk about the same ontology of a theory, but we will have different construals of that ontology. This point has also been made by Arthur Fine, who calls it the core position that realists and non-realists share, so both accept the results of scientific investigations as in some sense true, even if they give different analysis of the notion of truth. And there is another point that you can make here about how realists might interpret these ontologies differently, but I will skip that and just go to the conclusions in the interest of time. So I've illustrated the idea of ontological emergence as a non-commuting diagram between these two maps, interpretation map and linkage map. The interpretation of the massless particle theory is different from the interpretation of the massive particle theory with the mass set to 0. So we get really different interpretations when we do that. The account is metaphysically weak, as I argued towards the end, because I have focused on the basic question of when ontological emergence obtains, rather than about further metaphysical notions like causality, also, which I haven't, which do not appear at all in this framework. And the framework can be applied in other examples, and that's something that I have forthcoming work on. So thank you, and I look forward to it.